Okay, we should be recording. Um, cool. Okay, well, let's get started. So, you guys know I like to start these lectures with a meme or a cartoon or a design fail that just kind of reminds us of what we're doing in 4501 and why we're here and to give us some perspective. And so this one is hits me particularly close to home for a kind of a subtle reason. So there's an obvious design fail here, and then there's one that's maybe not so obvious. But this is two design fails wrapped up in one. Wrapped up, haha, no pun intended. So these are bananas, right? And you guys hopefully know enough about bananas to recognize the bananas come in their own wrappers. And so it seems very unusual to me that they would that a store would put bananas inside a plastic wrapper to then sell them, because it's just extra time and cost and material to put the banana in a wrapper. And okay, maybe you could argue, well, these bananas are marked with sell by dates and barcodes and all this information, and for that you need a wrapper. But then I would come back and say, well, is that really the best form factor? Or could you instead just put a sticker on the outside of the banana that contained that information, which maybe would cost less and not do double duty of basically wrapping up a piece of fruit that's already sitting in its own wrapper. So that's sort of the obvious one. The maybe not so obvious one arises from my doctoral research 1,000 years ago at MIT. And some of the work that I did looked at transport of water vapor through micro and nanoporous barriers that were made out of polymer. And I'm pretty certain, given that I'm familiar with this material that the bananas are wrapped in, that it's a non-porous polymer. So it's not, at least on short time scales, permeable to organic molecules. And the reason that is so offensive, at least to me, is bananas as they ripen will off-gas ethylene, which then promotes the ripening process, right? So you might have seen the trick of, if you have, underripe fruit that you want to ripen quickly, you put it in a sealed container with a banana, and that causes the ripening process to accelerate. And that's because the bananas off-gas this organic molecule, this gas that basically accelerates the ripening process, and that is a self-ripening mechanism as well. So the banana here on the far right looks like it's, maybe it got another hour or two of good life left in it, and then it's probably too squishy to even sell. And I think part of that is probably because whoever decided to do this put the bananas in what I think is non-porous plastic material that doesn't have any vents for the ethylene to get out. And so they're literally sitting in their own ripening gas, very quickly accelerating towards being too ripe to sell. So that's maybe the non-obvious, but kind of more technically subtle design fail. Interestingly, we talked before about intellectual property, but I don't know if it was this section, but one of the sections was asking me how many patents I have, and I sadly answered the question, well, I've tried to get maybe half a dozen different patents in my career, and I've never actually been successful. One of the patents that I tried for at one point in time, when I was doing that micro and nanoporous barrier transport research, was actually a material that was a nanoporous material, and one of the claims was that it could modulate the ripening rate of fruit. So the idea was that there were these little, like, nanometer scale pores that were just big enough to let ripening gas in and out. And the idea was that by just very slightly changing the temperature, you could actually get the pores to shrink, or by increasing the temperature, you get them to grow just a little bit. And so you could, just by putting the bananas in a slightly hotter environment or a slightly colder environment, in one of these porous bags made out of this porous material where the pore size changed, you could modulate the rate of ripening by just very subtle changes in temperature. So that was actually one of the ideas that I attempted to patent, and sadly was not successful. But anyway, that's that's why I know so much about banana ripening, is I did a lot of research to try to figure out how that product would work. So anyway, just another interesting design fail. You sort of wonder why whoever did this felt the need to put a fruit that's already in a wrapper inside another wrapper that then accelerates the ripening process to the point that the fruit is going to over ripen before you can actually manage to sell it. But anyway, just another sort of interesting thought about, why people make the decisions that they make. So anyway, today's presentation is going to be hopefully not the full class time. I know a lot of people have got questions about the PDR. You guys have got one more week to go. The preliminary design report submission is a week from today at 10 p.m. So I do want to wrap up about 10 minutes early to give people a chance to ask questions. And happily, this presentation is one of the shorter ones. But so we are now in the finalizing design module. And so this is a new module for us. And I love the title of this talk. It originally was just selecting OTS versus custom parts. But over the couple of years that I've taught 4501, it's now expanded into this, sort of nursery rhyme mouthful of Maslow's hammer, the Birmingham screwdriver, and death by McMaster car, selecting OTS versus custom parts and quantitative engineering analysis. So we'll skip this slide because we started here to get the presentation going. Before I jump into kind of the meat of the topic, I did want to just spend a moment kind of answering the question of what happens in design reviews. I've gotten a number of questions from various groups that are like, what's a design review? So just give me a moment to talk about that, and then we'll jump into the main subject. So, so the design reviews are going to occur starting next week. They're going to run all next week and then all the following week after that. Let's see, does there want to be a space here? Oh, there does. Okay, there we go. The joy of PowerPoint. Okay. And each team is going to be asked to participate in 2 design reviews, and I'll explain what those are in a second. So in a design review, and this all happens via Zoom, right? So it's all done online. So what happens in the design review is that your group first shares with us the hedgehog concept that you guys have developed that by now hopefully is very strongly influencing your design decisions in a particular direction that is consistent with the hedgehog concept. So we'll ask you first what that is. And then after we've sort of got your hedgehog concept digested, then we'll ask you to walk through a representative CAD model for your system. This does not need to be the final CAD model that you submit for the preliminary design report. It just needs to be representative. So all of the major parts are there. They're all kind of assembled in a way that's representative of how the final product will be assembled. We're not yet worried about things like fasteners, things like fittings, things like hoses, wire runs, anything that's sort of secondary to the structure. If you've got that stuff in your CAD model, that's awesome. No need to take it out for the design review. But if you don't have that stuff yet, don't worry. We're not yet going to be nitpicking things like fasteners and wire runs and that sort of stuff. It's mostly the big dimensions of the most significant parts and how they all assemble together that we're interested in. So we'll let you kind of walk us through the subsystems, and then like 5 minutes, 10 minutes, 10 minutes into it, we will start asking questions and have kind of a back and forth discourse, really focused around the question of like why things are the way they are and not some other way. Now, when I say we, who's we? So we is myself, Dr. Nimi, and probably Dr. Carol Chesney, who is going to be the 4501 instructor, at least the heir apparent 4501 instructor in the spring. So the 3 of us will likely be there. And then also the teaching team. So our ULAs and our fellows, 2 or 3 of them will also be present in the design reviews. So you're probably going to be interacting with a group of somewhere between 4 to 6 people, depending on, just the time of day and who's available. And, really, I want you guys to think about this, and probably the whole class at this point, really, as we're all on the same team, right? It probably doesn't feel like that. We're, forcing you to do all this work and we're grading it. And, there's still sort of this combative instructor student kind of dichotomy in the class, but that kind of barrier really after the PDR breaks down almost completely to the point that we are all on the same team, right? So remember, we have an external customer, Professor Sheffy, Professor Greenslip, Professor Trainum, and the expectation is that by the end of 4502, we are going to deliver to them a population of very well-designed functional heliostats that meet all of the customer needs that they provided to us. And part of that is on you guys, but a big part of that is also on me and Dr. Nimi and the 4501 teaching team. So really, all of us are on the same team trying to satisfy the needs of the customer at this point in the class. And so, if you start thinking about it that way, as opposed to some sort of kind of combative interaction, it'll probably go a lot smoother. And we're going to make some suggestions, and they're not meant to be punitive or draconian. They're really meant to avoid what I've seen happen over and over again, which is teams will forget some really important thing in their overall product design, and then they get in with the panel, right? The final panel in the last week of class, and that includes our corporate sponsors, that includes our alumni, our stakeholders, design faculty, our customers. We have had panels as large as 25 people evaluating, student groups of 7, 6 people. So you guys, at least in terms of numbers, oftentimes will be outmatched by 2 or 3 fold by the size of the panel. So what invariably, well, if things don't go well, what ends up happening is that some member of the panel will identify some very tiny nitpicky little thing, right? So like, oh, why is this screw going through the hole in this way and sticking out the other end in a way that it could rub on this other part, right? Just, I'm making stuff up, but some very trivial little thing, which all of a sudden starts to feed the doubt of the panel that the design process was done with professionalism and competence. And then all of a sudden you get the feeding frenzy, right? They'll just descend on that one little mistake and start asking a bunch of questions about why is the part this way, and why are the dimensions this way, and why is the material this way. And it really takes away from kind of the value of that overall final design review, because it turns into the committee or the panel basically nitpicking something small, some just small mistake in the CAD model. And so, at least for this first time through for design review 1, what we're really interested in doing is just sort of eliminating, or at least reducing, the possibility of kind of one of those little silly mistakes creeping through and being present in the end when you guys give your final presentation, because we don't want sort of those glaring mistakes still sitting out there in space for the panel to pounce on. So we want your designs to be really neat and clean and well thought out, and not have any kind of loose ends hanging out there. So so those are the types of questions that we're going to start asking. Questions about why is this the way it is? Why is this part sticking out over here? Could you actually assemble this thing the way that you've described it to be assembled? Could this part be made out of something else? You've got 2 parts here that mismatch each other. How do you reconcile that? Can this part actually be fabricated, right? There's a tendency for students to draw things on SolidWorks and then discover that they cannot actually be fabricated as drawn. So those are the types of questions that we're going to ask, and it's really just a back and forth discussion, not, again, meant to be draconian or punitive in any way, but just to help you guys give the best oral presentation that you can to our panelists in the last week of class. So we're going to go through this twice. We're going to have design review 1, which is going to last 50 minutes. And I've taught the class for 2.5 years now, and 50 minutes is the right amount of time. If we have more time than that, we sort of, don't use the time well. And if we have less time, there's usually still stuff that you want to talk about at the 45-minute mark, and time expires. And so these 50-minute sessions correspond nicely with a 50-minute class schedule. And so we're going to have 6 meetings in this coming week that correspond to class time. There's 13 groups. And so there's going to be 7 additional meetings, which are outside of class. 7 plus 6 gets us to 13. And so I apologize. I know that you guys have got other things going on, and it's, very jarring to ask you to be available outside of regular class time. But there's really no other way to do this and give every group an appropriate amount of time other than asking you to meet with us, for 50 minutes for at least 7 groups, 7 of you, 7 groups, 50 minutes outside of class. Now, the trade-off is that you only have to meet with us once during your design review period that entire week, right? So there's going to be no regular class next week, no regular class the week after, just the design reviews. And your group only has to be with us for 50 minutes next week and 30 minutes the following week. The rest of the time is yours. So use that time to finish up your PDR, start on the assignments that are going to drop on Monday, which start to become the final poster and the final presentation type assignments. You guys will see those on Monday. The second design review really only needs to be 30 minutes long. I found that 45 or 50 minutes is too long for that second design review, but 30 minutes is just about right. And so 30 minutes is a short enough time that we can actually fit 2 of them more or less into a class period, right? Class periods are 50 minutes. 2 of these together gives us 60 minutes. And so what I'll ask you guys to do, I'll put the signups up next week. What I'll ask you guys to do is sign up for sessions that end up starting 5 minutes before class or run 5 minutes after class. So that extra 5 minutes before and extra 5 minutes after gives us 60-minute blocks. 2 30-minute presentations fit in a 60-minute block. So, again, I know you guys have got other things to do, and coming to class 5 minutes earlier, being held 5 minutes over is an inconvenience, and I appreciate that. But I found over time, having now done this for 2.5 years, that's really the best way to get everybody the design review feedback they need in a timely fashion. So I'll just ask you to please be patient, and please just trust that starting class 5 minutes earlier, ending at 5 minutes late for design review 2 actually leads to a better outcome than if we try to do it some other way. So here's a screenshot of just what happens at a typical design review, just to give you kind of a sense of what they look like. So here's me, right? The look of frustration on my face. And then here are a number of students. There's at least one teaching assistant in here as well. And all we're doing is just asking the students to walk through a CAD model of their design. So this particular model was from summer 2020. The students were working on 3D bioprinters, which I'm going to talk about a little bit more here in a second. So probably good to just get sort of at least marginally oriented with how these things work. So there's a needle that goes down here. That's this white thing. And the needle deposits bio ink, which is typically like a living cell laden liquid-like solid into a petri dish, which is sitting on a microscope stage. And so you're actually watching in real time as these cells get deposited in some sort of well-controlled 3D pattern inside a petri dish, and you're imaging it with a microscope in real time. So you can see here, there's an X stage, a Y stage, and a Z stage, which are all sort of externally actuated by these flexible rods that come out and turn those screws that actuate the stages. And then the whole thing mounts onto a confocal microscope, which is this sort of see-through element here, is the mounting stage for the confocal microscope. So we're just looking at their CAD model, going through and checking that there's no interference between the parts, that if you turn these screws too far one way or another, that you're not going to just unscrew something and cause the whole thing to fall apart, that the needle is long enough to get down into the petri dish, that all of the plumbing connections are such that the pipes themselves or the tubes themselves won't pop off when you pressurize them. Just, kind of every little nitpicky thing that you could think of. And we're just walking through this design systematically to make sure that it will work the way that the students claim that it'll work in meeting all the customer needs. So we will subject your heliostat designs to a similar level of scrutiny as we walk through design review 1 and design review 2 with you guys in the next 2 weeks. The final element of this is the assignment associated with design reviews, which I call design review contracts. And I've got contracts in quotes because they're not really contracts, right? It's not like some legally binding document that you guys sign, that gives me your firstborn child if your heliostat doesn't work the way that you promised, right? It's not that at all. A contract just seemed to be the appropriate word for what these represent. So as we walk through the design reviews, the panel is going to make a series of suggestions for improvement, again, in preparation for you guys to really be just completely on the ball and, really, really, really well thought out and well rehearsed for your final design presentation. So, we're gonna roast you a little bit in the design reviews, but it's not, again, meant to be draconian or punitive. It's meant to be beneficial so that you don't end up in that same situation when you're in front of the real oral presentation panel. So as we're going through this process of sort of asking questions and, roasting various elements of your design that could stand improvement, I'm going to be working in the background to produce in Canvas a unique design review contract. So it's just a list of items that the panel comes up with that we would like you to at least consider for the following design review. And I say here 0-point assignment, and I'll explain how it ends up getting graded here in a second. So this list of things that we'd like you to check on, this design review contract, it'll be different and unique for every group. And I'll put it in Canvas for your group and connect just your group to it so no one else will be able to see it. And it'll drop, hopefully a day or two after, at the most, after your design review. And then the idea is when we do design review 2, the follow-on design review, the first thing that we're going to do in design review 2 is ask you point by point how you addressed the suggestions given in design review 1, to really just get a sense that you did listen to what we were saying and did at least consider our suggestions for improvement. Now, if our suggestions for improvement are incredibly stupid, which in some cases they will be, because at this point, you guys are the subject matter experts, right? You know more about your design than we know about your design by a lot. And so we might suggest things that are just silly given, what you guys know about your design. Even if the suggestions are silly, we ask that you at least consider them and respond to them in a professional engineering way, which is to simply say, we thought about that, we did this calculation, here's the result of the calculation, your suggestion actually isn't great for the following reasons, right? It causes this part to break, it causes this subcomponent to not operate the way that it was expected. The way that we originally designed it is better for the following reason, right? Just, whatever you want to present to us. But please at least consider all of the suggestions, even if they're silly, and either implement them or kind of explain why they're not actually good, valid suggestions. So that'll be design review 2. And then here's the assessment part. So you guys still have in front of you the FDR, the final design report. And so in the final design report, there will be a section where we ask you how the feedback provided in your design review contracts was addressed in the final design of your heliostat project. And so this is where the points actually get assessed. So we will actually read, and these don't need to be long, right? So like 2 paragraphs, 3 paragraphs at the most per design review, maybe 1 page of narrative. But do just summarize in those paragraphs how you address the input from the design review and how it informs the final form of your heliostat product. And within the context of the FDR grade, there will be a subset of points allocated specifically for that section on how you fulfilled your design review contract. So that's ultimately how this 0-point assignment will ultimately be assessed. It'll be assessed in the overall context of the grading for your final design report. Okay, so I think that's all I want to say about that. Let me pause there and ask if anyone has questions about what happens in design reviews. No questions. Okay, well, while you guys are thinking about your questions, let me bring up, this is Canvas. Let me go. Okay, so here's the homepage, the course homepage within Canvas. If you go to, you could access it either through pages or modules, but within modules, there should now be a week. There it is. Week 12, which is this coming week, within module 9, which is design reviews. So a week 12 page. And if you click on the week 12 page, I haven't completely fleshed it out yet. But on the week 12 page, each time slot, date, time slot, and URL for each of the groups that signed up for those time slots, those are all listed. I haven't done them for Friday yet. I still have to do that. But Monday and Wednesday, these are all fleshed out. So this is how you figure out where you have to go during the time period that you signed up for design review 1, is you just go to the week 12 page within Canvas, and then just click on the link that is associated with your group and your meeting type. So that's how you get to the meetings. I initially tried to do it in Zoom conferences, but it just became kind of unwieldy, and there was no way to tell like which meeting time corresponded to which group. And so I just decided to do it through page or pages rather than through Zoom conferences. So anyway, Friday will be filled out, hopefully before the end of the weekend, but you guys are the last 4 groups to go. So we still have a little time to flesh those out. Anyway, okay. So any questions on design reviews?
You said how many design reviews will there be total?
Each team will have 2.
Okay, so when you said design review 2, is that the same thing as the final design review that you talked about?
Nope. Design review 2 is the 30-minute. Here, let me pull the slides back up. There we go. Design review 2 is the 30-minute design review that will happen in week 13. The final review that I was talking about, the final oral presentation, that happens in week 15, and that's in front of the entire panel of customers, sponsors, design faculty, alumni. That's the one where you could end up with 25 people in your session. So okay. These design review 1 and design review 2, that's just us.
All right. I think I just confused the terms. Thank you.
Yeah, no, that's okay. I'm probably using the same term to mean multiple things, but the terminology is not incredibly sophisticated yet. So, okay. Any other design review related questions? No. Okay. Then, so let me jump into kind of the meat of what I wanted to talk about today. And this again won't take a super long time. It's the idea of Maslow's hammer, the Birmingham screwdriver, and what Dr. Nemi and I sort of jokingly refer to as death by McMaster Carr. And this comes down to your selection process between off-the-shelf parts and custom parts. And as you guys know by now, having interacted with me for almost a full semester, I don't like to waste time in class with sort of boring lectures that aren't beneficial for you in your projects. And so this section of the lecture kind of kills 2 birds with 1 stone, in that within the preliminary design report, there is a preliminary system design analysis section, and there's a subsection 3, which requests additional engineering analysis of selected design to refine parameters and develop CAD models. And then I've got it underlined here, we require at least one quantitative engineering analysis required for each subsystem. And so I'm going to talk about Maslow's hammer, but I'm also going to talk about it in the context of what is a quantitative engineering analysis? What is it that we're actually looking for when we say that? Because I've had a lot of questions about are these engineering analyses like RAR type analyses, or are they back of the envelope orientation calculations like we did in the CDR? And as you'll see, they're the former. It's more RAR type calculations that we're really looking for in the preliminary design report. So I show you this image because this is another 3D bioprinter. This is from fall 2019. They call this the turbo cell printer. So this was the final project for 4501 that semester. And you can see it has all the similar elements of the 3D bioprinter that I showed you before in the context of the design review. There's this sort of white thing here, which is where the 3D bioprinter mounts onto the microscope. There are these motors that turn these kind of flexible shafts, and the flexible shafts then in turn turn screw mechanisms inside the 3D bioprinter, and the 3D bioprinter moves in XYZ, and you could kind of see it peeking out here. There's this little needle, kind of a yellow syringe tip, and then a needle coming out of it, and the liquid-like solid laden cells, which are deposited in a petri dish to create this 3D biostructure that this printer is designed to create. Those cells come out of that syringe. But how do they get there to begin with? Well, there's a reservoir of them, and the fluid has to be pumped with the cells in it out of the reservoir and then pressurized so that it can be forced through the syringe needle into the underlying medium in which you're doing this bioprint work, this 3D bioprint work. And so the focus, at least one of the subsystems that was the focus of a lot of anxiety for the fall 2019 students, was the cell deposition and extraction subsystem. So the system that effectively pressurizes the liquid-like solid and pushes the bioink, the cells that you're printing with, into the 3D bioprinter, ultimately through the nozzle and into the petri dish. So this little fellow that I've circled here in orange, that's going to be the focus of an analysis that I'll show you guys in a moment. But we'll come back to this. So what is Maslow's hammer? Well, this idea has been attributed to a number of different people over time. Mark Twain, Samuel Clemens, is actually supposed to have said, if I have a hammer, every problem starts to look like a nail. But if you dig really deep into kind of the historic quote literature, it turns out that Clemens did not actually say that. So the first time that I could find anything approaching this idea that if you have a hammer, every problem starts to look like a nail, was put into print, was in the text Toward a Psychology of Being by A.H. Maslow in 1962, in which Maslow said, quote, I suppose it is tempting if the only tool you have is a hammer to treat everything as if it were a nail, right? So hence Maslow's hammer, right? Here's A.H. Maslow, and here's the hammer that he's talking about. So what does he mean by this? Well, it's the idea that if you have something that has been sort of tried and tested and proven that solves a particular type of problem, even if you encounter problems that don't fit into that particular subset of problems, you find a way in your mind to morph every problem that you encounter into one that can be solved by this tool that you've got, right? So another way of thinking about this is the Birmingham screwdriver. So urbandictionary.com defines a Birmingham screwdriver as a hammer, right? Usually used on delicate devices when a real screwdriver would be better. And then they say C, percussive maintenance. And so I've got this little funny cartoon here where you've got what's clearly a threaded screw pleading for his life, saying, wait, hammer, no. And then the hammer is saying, quiet, nail, right? And you see what's going to happen, which is this hammer is going to try to pound this threaded screw into the underlying surface, right? Hence the Birmingham screwdriver, right? This hammer is a Birmingham screwdriver. And the thing that I like so much about this cartoon is that the hammer has consciousness and has lost perspective and fails to recognize that this little thing is actually a screw and not a nail, right? He's actually calling it out, quiet, nail, and he's about to pound him in. So it's that sort of loss of perspective that I think really embodies Maslow's hammer and the Birmingham screwdriver. And the reason that it's important to just be aware that this is a type of bias that creeps into the design process is that we as engineers, especially now in 2021, basically have our own versions of Maslow's hammer and the Birmingham screwdriver, which is McMaster-Carr and Amazon, right? So as you guys are in the process of developing your preliminary and then ultimately your final designs, you're designing in intimate detail each individual part, right? People have asked me, how much calculation do I need to show that I've done, an engineering and analytical calculation for the preliminary design report? And my answer is always, well, you have to show us that you've done enough calculations to explain why a part is the way it is, right? Why is it made out of the material that it's made out of? Why is it the dimensions that it is? Why does it have the tolerances that it has? Why are the features the way that they are? Why are the features located in the place that they're located? What are all of the other possible options for how that part could have appeared? And why are all those other options inferior, as evidenced by the fact that you didn't select all those other options? You selected the part that you've now presented me with as kind of your final version of this part. So in that process, there's a very strong inclination to use something like McMaster-Carr or Amazon to specify an OTS off-the-shelf part in lieu of a custom part. The reason for this is that OTS parts are often perceived as being less expensive and easier to obtain than custom parts, right? You just go to Amazon and buy it, or McMaster-Carr and buy it, and it shows up on your doorstep 2 days later if you have Prime. And so what wasn't that easy, right? It's like having the easy button. Wasn't that easy? I didn't have to actually manufacture or fabricate anything. I just went to McMaster-Carr, found the part that I needed, pushed the button, paid for it, and it showed up on my doorstep. So initially that feels like a very good and very safe approach. And sort of sadly in DML, because the catalog of parts that you guys had available to work with was finite, I feel like in a lot of cases, DML actually creates this mentality of, I'm just going to design by digging through MasterCard until I find what I need. There are some drawbacks to this approach. So one is that it needlessly constrains design options, right? Which is kind of the Maslow's hammer view of it, in that you've got this solution, which is the OTS part that you found on McMaster-Carr, and that very quickly forces your brain, or at least compels your brain, to collapse the design space down to that one solution, right? So if you have a hammer, every problem starts looking like a nail. So McMaster-Carr kind of using it without realizing that this bias is there, collapses all of your design thinking down into one solution, which is the one that you happen to find on the MasterCard website that seems really easy. It also forces unwanted compromises, which is the Birmingham screwdriver, right? Birmingham screwdriver is, I know I need a screwdriver. What I have available to me is a hammer, and I'm just going to use the hammer to pound in this screw in hopes that it'll behave like a nail and that that'll be good enough. So my advice, my plea to you is, especially if you're trying to create a novel function, so a function that's not something like fasteners, washers, motors, DC motors, piping, tubing, sort of the standard stuff, which McMaster-Carr or Amazon is a perfectly good place to go to find parts that carry out some standard function. But if you're trying to do something that's not a standard function, that's something novel, then please consider custom parts first and foremost before you jump into McMaster-Carr or Amazon to try to find something off the shelf, because chances are that custom part is not going to be in these sort of general catalogs, and you're going to be either constraining your overall design space or making some sort of unwanted compromise by purchasing an OTS part when you should be designing your own part instead to fill that need. So that's really what I want to say about Maslow's hammer, Birmingham screwdriver, and death by McMaster Carr. So let me pause there before we transition to the third part and ask if anyone has questions about those ideas. None? Good to go? Okay. All right. So then the last thing that I want to do is just give you an example quantitative engineering analysis of the type that we would expect to see in the preliminary design report. And I'm not going to, this is a fluids analysis, so I could spend a whole semester talking about this analysis. You'll see it's incredibly cool. I just want to give you guys sort of a broad brushstroke overview and then have a little time at the end for questions. We've got about 8 minutes left. So we should get through with a little bit of time left over. So this was fall 2019. This was one of the microbial printers. And we're looking at the cell deposition and extraction subsystem, which is this system that I've circled here in light blue. And in that subsystem, there was a component, and that component was the centrifugal pump. And the purpose of the centrifugal pump was to satisfy the customer need statement, which when quantified basically worked out as 1 microliter per minute of liquid water has to be pushed through a 1 meter long capillary tube with a diameter of 1 millimeter, right? So there's this tube that sort of starts at the pump and ends here inside the 3D bioprinter. And it turns out that this run of tube represented the largest pressure loss of any of the other fluid loss mechanisms in the system. And so they ended up wanting to make this, sort of as short as possible, while still putting the pump and the motor that runs it kind of off of the microscope stage, so it wouldn't cause vibration. And so our goal is 1 microliter per minute through a 1 meter long capillary tube with a diameter of 1 millimeter. So they ended up coming up with this really cool centrifugal pump. Here it is, at least its final rendering. So the front and back housing were going to be held together by screws. There was going to be an impeller on the inside, which I'll show you in a second, sealed by an O-ring. We were going to make it using kind of a photolithographic 3D printing technique via photocurable resin. So this is a blue photocurable resin that could be 3D printed. Manufactured using digital light processing. Okay, so that's a photocurable resin process. It did need to have, as part of the customer needs, 1/16 inch PTFE tubing attachments both to the inlet and the outlet, so that it can attach to conventional tubing in the laboratory. So hence you see the barbs to accommodate 1/16 inch PTFE tubing. Hose barbs ensure that the pressure of the hoses would hold them in place so that the hoses wouldn't pop off as this thing was pressurizing up to the pressure needed to move the fluid through rapidly. And then the materials were chosen so that this little mini pump could be sterilized with bleach or with ethanol as per the customer need statement. So for those of you guys that have taken John Abbott's thermal design class, you might be in the process of designing a pump impeller. And so that's exactly the training that this group used, that a lot of them in this group had already taken Abbott's class. And so they just took what they learned in Abbott's class about how to design a pump and just shrunk it down to a viable size scale for the 3D bioprinter. So the impeller compresses against an O-ring on the back, which prevents leakage around the seal. We've got radially swept blades, allowing enough room for cells to pass through channels between the blades. So the channels between the blades are sort of these triangular shaped channels. There's enough room for kind of a cell to fit in there without getting stuck, which prevents the cell from then dying and contaminating the system. And the outer radius of the blades, which was set at 2.75 millimeters, was determined using Euler's pump equation, the desired flow rate, and the rational rotational speed. And so the students started out with this analysis really to try to answer the question of how fast does this pump have to turn? How fast does the impeller need to turn in order to get this pump to achieve 1 microliter per minute of this liquid-like solid material running through it, against the pressure loss of a 1 meter long capillary tube at 1 millimeter in diameter. So they started out with a control volume, and from fluids, they made a number of assumptions. So no minor losses, no elevation change. The water is going through the system as liquid, making it incompressible. They assumed, at least initially, that the pump was 100% efficient. It didn't produce any heat. It had 0 adiabatic efficiency, or I guess I should say 100% adiabatic efficiency. The capillary tube is made out of a perfectly smooth surface, which makes the fluid mechanics easy. And the tangential fluid velocity inside the pump is 0 because they intentionally designed it to be a centrifugal pump. So those are the underlying assumptions in the analysis. Here's the analysis itself. So they started with the Darcy-Weisbach equation, which gives the pressure loss in a pipe as a function of the friction factor, and then some geometric parameters, including the length of the pipe and the velocity of the fluid running through it. They decided the flow is likely laminar, so they went through the process to calculate the Reynolds number based on a volume flow rate, the Reynolds number, and determined the Reynolds number is much, much smaller than the turbulent transition regime. And so the fluid flow is very likely laminar. Given that the flow is laminar, we can go to Moody diagram and use 64 over the Reynolds number, which is just a straight line, this one on the Moody diagram, to pluck out the friction factor for a particular Reynolds number. So I had them calculate the Reynolds number, and it's 1.4, and use that to back out a friction factor. And the Reynolds number is pretty small, so we're actually up here in this regime of 0.09 to 1 as our friction factor. They plugged that value in, and out popped a pressure 36.58 pascals. That's now the pressure required to overcome the pressure loss in this 1 microliter per in this 1 meter long tube, 1 millimeter in diameter, with 1 microliter per minute of liquid water running through it. So that was a pretty good start to give us just a sense of the insanity of how big this number is. So having finished the delta P calculation and finding the friction factor, then they started looking at the rotational velocity. Would this thing basically destroy itself because it was spinning so rapidly? How fast does it need to spin to maintain those parameters? So they used the Euler turbine equation. They did an energy balance. They converted the energy balance into velocity vectors using vector summation, and ultimately inserted the mass conservation equation into their overall expression to pop out an expression that relates the change in pressure to the viscosity to other physical parameters of the pump, right? So these are just geometric parameters, angles of blades and widths and distances of blades and so forth. Took the blade design information from John Abbott's class and used it to find the rate at which this this pump would need to turn to generate the pressure required to push the fluid through at the previously stated volume flow rate. And it worked out that rotation rate was 2,295 RPM, which is excellent because that is a rate that's achievable within commercially available, inexpensive DC motors. And so they basically went through this entire analysis to show that a DC motor does exist that can make this pump function as expected. So that's kind of a representative engineering analysis that I'd be interested in seeing from you guys. 1 per subsystem is the minimum that we're expecting. So I was super excited about this. Most of the other solutions that students came up with did not meet the customer expectation of 1 microliter per minute. And so this seemed like a really good idea. When the students then presented to the panel, any ideas what the key criticism was?
The size,
Okay, yes, and what do you mean by the size?
uh, maybe it was too small to manufacture easily.
We could manufacture them without too much trouble. It was the size mismatch between the 3D printer and the motor. So this motor sitting
Oh.
behind it is the smallest DC motor that we could find
Oh.
that would turn at 2300 RPM. So you get a sense of the size scale.
Yeah.
And the concern was that this motor would vibrate, and even just a small vibration as it was turning would be enough to completely destroy the seal inside inside the turbine or inside the pump. And so after that feedback from the panel, sadly, this little pump did not end up getting selected to propagate forward into 4502. So it ended up, sort of dying on the operating table here. Nonetheless, I think of this as a success story, right? Even though in the end it ended up not getting selected by the customer for this issue of dealing with sort of the vibration created by attaching a really large shaft to a really small pumping shaft. But it did satisfy the expectation of an engineering analysis by giving us a sense that the RPM that you have to turn the motor at 220 or 230 or 2200 or 2300 RPMs was completely achievable and reasonable within the commercially available off the shelf DC motors that the students were considering. So that was the level of analysis that we were looking for, just to prove that this thing would work the way that the students expected it to work, at least in the context of the fluids, the thermodynamics, the mechanics, and so forth. Dealing with the size differential and the vibration didn't cross anybody's mind, but that was the ultimate death toll for this idea. So anyway, that brings us to the end. Can I answer any questions related to the actual topic? Maslow's hammer, Birmingham screwdriver, death by McMaster car, custom versus OTS parts and engineering analysis? Nope, everyone good? Okay. I left this in there in case I ran too short for another engineering fail to talk about, but we can talk about this next week. So I'll leave this for another time. So with that, let me stop sharing. Class is over effectively. I appreciate your patience sticking around with me for a couple of minutes so that I could wrap that up in a holistic way. If there are any final questions, now is the time to answer. Well, to ask, and for me, hopefully to answer. And if you guys have no questions, then feel free to go. Class is over. We'll see you in the design reviews next week. But I will stick around and answer any questions about the class if you guys have them.
I just wanted to double check something.
Yeah.
My group spoke to one of the TAs in office hours this week, but I just wanted to check with you
Sure.
while I was here.
I'm ready.
For the IP disclosure assignment due tonight, you don't want us to go too in depth about it, right? To do a surface level look at the previous literature and answer the questions posed in the assignment description, and that's all you really want from us for this assignment?
That's it. Yep.
Okay.
Yeah, it doesn't need to be super detailed. It just needs to be enough to demonstrate that you've practiced submitting an IP disclosure. And if you feel like you've invented something, we'll circle back around again. So I'm going to go through all of them and see if anybody has a legitimate bona fide invention that they want to disclose. And if so, then I'll reach out to you, and we might need to do a little bit more wordsmithing on the submission when we do it for real to the university, but it shouldn't be that much more. But yeah, for this, it's just almost a copy paste job from the CDR. It's almost that easy.
Okay. And then for the description section where it wants us to describe, would it be appropriate to just describe it, or should we include like pictures alongside it?
You can include pictures if you want to. The initial disclosure form to the tech transfer office, the UF tech transfer office, does not have a way of including pictures, I think, that I'm aware of. So that's optional. If you
Okay.
feel like it makes the case stronger, then by all means include pictures, but they're not required.
Okay, thank you.
Sure.
Hi, Dr. Trump. Just to go a little bit further onto the IP disclosure, when it says prior art, so is that we were thinking it was mostly just maybe like pictures from prior patents, and then maybe like a 2 to 3 sentence description of both that design and maybe how we either did something similar or different from it. But when you say copy and paste from the CDR, are you saying like almost a full literature review?
So, yeah. So yes and no. You guys already did. I hope you already did in the CDR a full literature review.
Right.
So
it just wasn't really particular to what our design ended up being after the down selection matrix. They were just heliostats in general. They didn't really apply to what mechanisms we ended up choosing. So we were going with a little more like applicable examples in the IP disclosure.
Gotcha. Okay, then yeah, you'll end up having to do a little more footwork then, along the lines of what you described. So we're looking for, I'm going to throw out a number here, maybe 5 examples of kind of prior art that's similar, patents, papers, other public disclosures. It's mostly so one of the benefits of having the tech transfer office as a partner in this process is that those guys have got patent IP experts that can go out and scour the entire available sorry, it's nap time. I only got a couple hours of sleep last night. This has been a bad week. Those guys are available to go out and sort of scour the literature for patents and papers and things that would ultimately be included on a patent application. They need kind of like a head start. And so I would say 5 is a good number, like 5 patents that are most closely related to this thing that you're disclosing. And what that'll do is just sort of give some initial guidance to the tech transfer office for the technologies that they should be looking at when they do their full blown patent and literature review. So, but you guys should not spend an enormous amount of time on that. It really should be like, a couple of paragraphs, no more than 5 previous inventions, and that's plenty good. If ultimately we decide that you guys have invented something, we might ask you to circle back and find a few more, but at least for this assignment, 5 is good.
Okay. So I think we have 5. I might just go back and expand upon what we wrote to be a little more than 2 or 3 sentence descriptions and kind of go a bit more in detail, kind of like we did in the CDR. But okay, thank you.
Yeah, that'll be fine. It's all any work that you do now, if ultimately it's found that you've truly invented something that requires a disclosure, will just mean less work later, right? So if you got the extra time and the bandwidth, it's perfectly fine to do it now.
Okay, thank you.
Anything else?
Hi, Dr. Trump. Can you hear me?
I can, yes.
Hi. I guess I got a question about the RUR type analysis that we would do for each subsystem. So say, for example, we're calculating like the wind load on one of the heliostats. Would that be more like a fluids type analysis, or would that go more into like, I don't know?
Yeah, wind load would be a fluids type analysis for sure. Now, so you don't need to feel compelled to do one of each type analysis for every subsystem. There are some subsystems that will, there's just no fluid analysis that you can imagine doing, right? So some of them will not lend themselves to every possible type of analysis. Thermal was another one, right? Where it's sort of hard to imagine some of the subsystems being viable for thermodynamic type analysis. So just do the engineering analyses that make sense to fully flesh out the part that you're analyzing. Don't feel compelled to like create an analysis that doesn't make any sense, if that makes sense.
Yeah, it does.
Great. Yeah, but yes, wind speed is a good one. And if you've capitalized on small size, which I hope everybody has, don't forget the boundary layer. I don't think anybody in the summer remember to do the boundary layer calculation, right? But if you've got a wind speed at 1 meter or 2 meters off the ground is a flat plate, right? And you guys know I hope you remember from fluids, how a boundary layer develops when the fluid is in close proximity to a flat plate. And so if the free stream velocity is 30 miles an hour at a meter or two above the ground, the velocity down close to the ground where your heliostats live is going to be quite a bit less than that, right? If it's turbulent flow, it follows the 1/7 power law. So remember that you guys might actually get a really, really nice advantage for making the heliostats small with respect to those wind speed calculations if you keep the boundary layer in mind. So just let me just throw that out there as a suggestion, because nobody did it in the summer. I was surprised nobody did it, but nobody did. So worth looking at. All right. Any other questions while we're here?
Would we be given, I guess, access to a rubric for the PDR, or how does that work?
No, it's the same story as it was for the RER and the CDR. We do use a rubric to evaluate, so that everybody's on the same page with respect to how grades are given. But we've played with this kind of in both directions for the past 2.5 years, and we've settled on. I think the best teaching practice is not to give a rubric. And the reason, and I know that that's annoying for you guys, right? It would be much nicer for you guys to see a rubric to see exactly how you're being evaluated. But the argument goes, and I think this is right, that 4501 is your transition from being students to being engineering professionals. For a lot of you, this is the very first kind of full-blown engineering project that you've really sunk your teeth into. And interestingly, this afternoon, I gave a presentation to our EAB, our engineering advisory board for the department. And one of the things that they mentioned in that meeting was that they did not want me to give you guys rubrics. There was one of the members actually was saying that, in the real world, when junior engineers are assigned a reverse engineering type project, the manager does not give out a rubric about, this is what we're expecting to see in this document. They will give you past examples, which is why we give you past examples of old RERs and PDRs and CDRs and so forth. But we want to get you used to operating in a world where you don't have a grading rubric, because that's the way that the real world works. And so that's kind of the 64,000 foot explanation. Another explanation that I've also seen that makes more sense from a pedagogical perspective, is that a lot of times, and I know this isn't you guys, but your peers, your colleagues will just treat the rubric as a bunch of check boxes, right? Oh, I've done this check, I've done this check, I've done this check, I've done this check. Oh, I'm good. I've got all the boxes checked. I'm now going to get an A on this assignment, and I don't need to do any more. So we don't want to encourage that sort of mindset in an open-ended design class. We want to make sure that you guys, you know, are flexible in your thinking and are sort of open-ended and open-minded in your thinking. And if there's something that you guys want to do in the PDR or the final design report that somehow doesn't fit into the box that a rubric would create, we want to give you guys the freedom and flexibility to do that. So that's yet another reason to not use a rubric, because it then prevents people from just sort of going down and checking all the boxes, and allows you to be, you know, much more like professional practicing engineers in the expansiveness of the analyses that you do. So sorry, that was probably a really long explanation for why we don't give rubrics, but there is a method to my madness. I'm not doing it just to be mean. I'm doing it because I think it's my belief and my experience is that it is actually a best practice.
Oh yeah, that makes sense. Thank you.
Sure. Any other questions while we're here? Okay, let me,
Dr. Trump, I have a question.
yeah, I'm ready.
All right, so it doesn't have to really do with the lecture or anything like that. Just when we submitted our the CDR,
Yep.
we only had one person in our group submit it.
Yes.
So everyone else in the group doesn't have like a grade in Canvas yet. And I was wondering if like there was something we should do about that. Like only the person who has submitted it in Canvas has the grade.
Oh. Okay, well, hang on. Let me stop recording because this is now